Hello, my people. I hope we're doing well today. This uh, this is the third video for the other four trig graphs. We're going to go ahead and do the same thing we did in the first two. We're going to go ahead and construct the parent, and after constructing the parent, we're going to do two. We're going to do two transformations. So. Remember that secant is defined as the reciprocal of cosine. So let's go ahead and graph cosine the way that we're used to graphing cosine. And then we're going to take that graph and use it to construct our secant graph. Okay, now cosine starts up here at 0, 1, and we know that it hits it has an x-intercept at pi over 2 and negative pi over 2. It comes down to its minimum at pi, which is negative 1, comes back up 3 pi over 2, and achieves a maximum again at 2 pi. Now, we know at pi over 3 it's 1/2, and of course that's the value that winds up being really helpful and convenient for graphing cosine. And so we're going to go ahead and just use those values to go ahead and get ourselves a reasonable graph of cosine. Now, this is arguably less complicated than tangent is, because tangent is one trig function over another. But you have two pieces of it, which makes it in some ways a little more difficult. But like tangent, we have cosine in the denominator, and we know, no matter what the numerator is, that when we have a 0 in the denominator, it's undefined, and therefore we're going to have asymptotes everywhere where cosine is equal to 0. And so we'll just go ahead and draw those asymptotes, and then we will get about the business of taking the reciprocal of those convenient values that we have for cosine. Now, the great thing about 1 right here as an output is that the reciprocal of 1 is 1. So that and that and that and all of the other infinite number of maximums for cosine are also going to be values for secant. And the same thing with these minimums down here, because the reciprocal of negative 1 is, of course, negative 1. Now, that's about where things end. So right here at pi over 3, we have an output value on cosine of 1/2. But that winds up being 2, right, when you take the reciprocal of it. And the same thing at negative pi over 3. Cosine of negative pi over 3 is 1/2. Secant of negative pi over 3 is 2. And it's the same thing for these values down here that have an output of negative 1/2. They get reciprocalized. Yeah, like I said before, not a real word. Don't use it in your college math classes. But I basically, I'll make up these words because I find that they're a lot more descriptive than the other ones. Okay. Now, I also know that at pi, if you want a really nice curve and you want a little more precision, then here at pi over 6, I have root 3 over 2. Root 3 over 2 is not easy to take the reciprocal of, okay? And actually, if you take the reciprocal of root 3 over 2, you get 2 over root 3, right? Which then you have to rationalize the denominator, and you get 2 root 3 over 3, or that's actually, probably a little bit easier to interpret as 2/3 of root 3. Now, if root 3 is 1.732, then it's basically just, it's shy of 1.8, which would be divisible by 3 really easily. 2/3 of 1.8 is 1.2. 2/3 of 1.732 is probably closer to 1.15 or something like that. So if you wanted to, you could probably, put something in here like this, although why would you? You can probably sketch it accurate enough without those points. You just need to know that it doesn't come, it does, just like sine and cosine shouldn't look like Charlie Brown's t-shirt. You need to have it curve, right? These are curves. And as long as it doesn't come out too steeply and look like a V, I think you're going to be just fine in terms of having a sketch that is accurate enough. Okay. Now, my secant graph are these curves right here, and we can see, of course, how how it being the reciprocal of cosine, we can see that relationship if we graph cosine first and use it to get our values. Okay. Now we're going to use that parent to do some transformations now. Yay! Okay. Alrighty, let's go ahead and make up a function. When you say we do something like, let's do one that's not too taxing on us. Let's do, how about 2 secant x minus pi over 3. Let's do plus pi over 3 minus 1. Okay. Now, that is 3 transformations, right? And of course, like always, we work from the inside out according to order of operations. The plus pi over 3 is going to take us to the left pi over 3 because x has to be pi over 3 more negative to compensate for that positive pi over 3. We have over here, we have a vertical stretch of 2, and then we're going to move that bad boy down 1. Now, since we've stretched and moved, that normal scaling that we usually use is probably not a good idea. On the y. On the x, we haven't really done anything, so the x can be scaled the same way that it usually is, and that'll be just fine. But on the y, because the minimums that are up here are at 1 on the parent, they get stretched to 2 and -2, and then it drops down to 1 and -3 when you drop it down 1. And the usual scaling that we do where it goes from -2.5 to +2.5 is just not going to show enough of the graph. So we'll sort of double that and make it -5 to 5 and make 2 boxes into 1 unit. And I keep mentioning this because it will be up to you to appropriately scale, the graph so that the significant points wind up being on the graph, right? Okay, so secant, we'll go ahead and do the parent real quick. And yes, you can do the parent real quick if you have it, sufficiently memorized. And the thing is that you don't even really have to memorize the values. You simply have to memorize it kind of as a pattern. That's the way that I've always done it. I don't actually self-consciously think about the numerical values of them. I just remember that, and that. And if it helps you to remember the values, if you're a values kind of person, that's fine. If you're a pattern kind of person like I am, memorize it as a pattern. But either way, you need to be able to sketch quickly, right, the parent so that you can get onto the transformed graph. Okay, and of course you won't be doing it in an array of magical colors. You'll be doing it just with a pencil. So just make sure, and I do it with colors on here just to make it sort of pop a little bit better so that you can see it on the video. But do the parent in dashed lines, and then do the transform graph in in, a darker solid line, okay? Now, just like all other transformations of trig functions, I'm going to take representative points, I'm going to transform them, and then I'm going to use the periodic nature of the function to extrapolate from there. Now, thankfully, we don't have a b value other than 1, and so we don't have any changes of shape on the horizontal. And so we don't have to worry about a change in period and a compression not only of the graph but of the asymptotes as they sort of squish in or stretch out from that x is equal to c line. I simply need to shift. Okay, so let's take this point right here. Let's move it over pi over 3. Then let's vertically stretch it, by 2, so it goes from 1 to 2 units, and then it drops down 1. Okay, let's take this value, pi over 3, 2. Let's move it over pi over 3. Let's stretch it by 2, so it goes from 2 to 4, and then it moves down 1. Okay. Well, I know that from this minimum right here, there is symmetry to these 2 points. So if this one is, over pi over 3 and up 2, it's going to be over pi over 3 and up 2 this way as well. Okay. Now, we've shifted everything to the left, pi over 3, and of course that includes the asymptotes. So this red asymptote has moved over to become this one, and so basically you just need to, give me new asymptotes. Okay. Now that right here is that that basically it's this red curve just moved over and stretched and then moved down. Okay. Now remember that on sinusoidal graphs, the sine and the cosine, that -1 right there would be your axis of oscillation. It's not exactly an axis of oscillation anymore, but it is helpful because it is your 0 value for y. Okay, this is my y is equal to d, and this time, of course, it's y is equal to -1. So when we take, we've obviously taken this original red and we've shifted it to the left. Okay, the rest of the transformations were done on the output. Okay, on the vertical. And so what we're going to do is we're going to take this one, this maximum value right here, this hump that comes up to this maximum, we're going to move it to the left, pi over 3. Then we're going to stretch it, right? We're going to stretch it away from the y-axis, the x-axis, to here, and then we're going to move it down 1. Let's take this point right here. Let's move it over pi over 3 to the left. Then we're going to stretch it, goes from 2 to 4, and then it moves down 1. Now, since we just transformed those 2 points, I can basically figure out where this one's going to go just because of the symmetry that has to exist between those 2 asymptotes. And I get a curve that looks something like that. Now, I have one full period right here. I have one full period. This right here, and now it's a little bit crowded, so that's why I like to use these highlighter pencils. And I'm going to take this single period and I'm going to extrapolate onto every period before and after. So this right here becomes this point, and this point as well. This, which happens between these 2 asymptotes, now happens between these 2 asymptotes as well. And actually, if you have a hard time seeing it, let me go ahead and sort of fill in all of those asymptotes for my eventual graph in the orange so we can see them. It is getting a little bit crowded in here. I'm trying not to mark too darkly so that nothing sort of clouds out anything else, but that has its own drawbacks. Whatever. All right. So we have that, and then I'm going to move over, and I also have it in this, between these two asymptotes. This is going to be here, and also here and here. This is going to be here, between these two asymptotes over here. And so what we get in our eventual graph, and here it's kind of nice, we can see 3 full periods, right? Okay, and that is your transformation. Yay! And of course, if you want to confirm whether you've done it correctly, you can go ahead and just, you know, take out your calculator and graph it and the parent function and compare them to each other. Now let's go ahead and let's do one more. This one we'll try and make it just a wee bit more difficult, just so we can see whether we truly understand the material. We have y is equal to, and on the last one we only had 3 transformations. Let's do, you know, 4 or 5 here. How about negative 3/2 secant of x over 2 minus pi over let's make it pi over 6, and then we'll, that's enough right there. That's fine. Okay, now in here that's a little bit of a mess. I know that I need to factor out my b value, and just remember that when you're factoring out a fractional or a negative b value, you just have to be very, very careful, okay? When I factor a 1/2 out of here, I'm going to get pi over 3, right? Because if I were then to redistribute that 1/2 across, I would get pi over 6. So I can now see my 4 transformations. I'm going to move it to the right, pi over 3. I'm going to horizontally stretch by a factor of 2. I'm going to x-axis reflect, and I'm going to vertically stretch by 3/2, 1/2, right? And remember that those two can be done in either order. It doesn't really matter, and the reason they can be done in any order is because multiplication is commutative. Okay. Now, if we're going to horizontally stretch by 2, you know, I guess we can go ahead and keep the same scale that we've had all along. When we're doing this 3/2 stretch, I don't want to, I guess I can go ahead and do it, you know, every 3 boxes is 1 unit. Because putting something in the middle of a box is fine. Putting something a quarter of the way through the box gets a little bit difficult to represent accurately. But if we go ahead and do it that way, I think we'll be just fine. Now let's go ahead and do the parent. And I'm gonna skip doing the asymptotes, since you know where the asymptotes are. I think the asymptotes are largely what got us into the trouble last time, in terms of it sort of crowding the graph. But you know, if you're just careful, you can go ahead and do this without the asymptotes. Trying to draw a graph and talk at the same time, always problematic. Okay. And just, you know, even though the asymptotes aren't there, just be careful that you know, don't draw past them. Okay, there is our parent, okay? And we know that basically there's an asymptote here, there's an asymptote here, there's an asymptote here, there's an asymptote here, and here, and here, right? I just didn't put them on there because I don't want to basically crowd up the graph. So let's go ahead and perform. Just go ahead and concentrate on that full period. We'll transform that full period, and then we'll extrapolate out from there. Let's go ahead and take this point. That's our most familiar point. We're going to move it over pi over 3. Now, when we move it over pi over 3, we need to remember that all changes in horizontal shape happen with respect to our new 0, and that x is equal to pi over 3 defines 0 now. Okay? So if I move over, my horizontal stretch is actually not going to do anything because you can't stretch 0. Okay? Now, with respect to its vertical displacement, it's not at 0. So I can reflect and stretch it. Okay? Let's go ahead and take this point right here. Now, and I find it kind of helpful to use these. Now, when I move over pi over 3, right, that's my new 0 line right there. So I've moved over pi over 3. I need to horizontally stretch, so it was 1 box away from the new 0 value. It's now 2. It is 2 units away from the x-axis, so it has a value of 2 in terms of its output. And then I'm going to take that 2 and I'm going to negativize it, x-axis reflection, and stretch it, turn it into -3. Now, if this is my maximum in between my new asymptotes, I know that there's going to be symmetry here. So if this goes over and down, you have a symmetrical point over here as well. Okay, let's go ahead and take the points on this portion and let's go ahead and move it over. Okay, now remember, I'm moving over pi over 3. I'm going to stretch it by 2. It's 3 boxes away, which is actually pi away from the new 0 value. And I'm going to double that, turning it into 6. I'm then going to x-axis reflect it, and I'm going to stretch it by 1.5. And that is where that minimum, because of the reflection, that maximum becomes this minimum up here. Okay, let's go ahead and take this point right here. That point right there, we're going to move it over pi over 3. It's 4 units away from the 0. We're going to double that, turn it into 8 boxes away. Now we're going to reflect it and then multiply it by 3/2, and it goes to 3. Now again, we have symmetry between the asymptotes, and so we have that. Now notice how this right here mimics this. If I were to sort of move this over here, it would be the perfect mirror image, and that's not accidental. Okay. Now remember that the new asymptote is going to be halfway between the maximum and the minimum. Or you can just basically think about it this way. The asymptote was here. If you move over pi over 3 and then stretch that out, the asymptote should line up right there at 4 pi over 3, right? And so let's go ahead and put that asymptote in right there. Now, the original period was 2 pi. Now, the new period is going to be 4 pi because you've stretched, right? And so it shouldn't surprise us that this right here is a distance of 2 pi, and then to the next one is going to be another 2 pi for a total period of 4 pi. And I usually like the scaling to be such that I can see 2 full periods, but I'm trying to make it big enough to be visible on the video. So please excuse me for not practicing what I preach. So basically 2 pi is 6 units. The next asymptote, of course, goes here. And we won't be able to reproduce this, but we can reproduce this over here. Halfway between the asymptotes is going to be my 0. Okay. And then I put those 2 points, and I'm going to get that. Okay. That right there is my transformed graph. Okay. I hope that that helps, guys. If you have any questions, please do shoot me a message. Um, some of the chatting functions on Teams is a little bit messed up because of permissions and stuff like that. So if you're having a problem on Teams, shoot me an email with your question, but also tell me that you're having a problem with the chat function on Teams. And the next video, of course, will be the same thing, but with Cosecant X. I'll construct the parent and do two transformations on that one as well. Bye.